If I had to choose to revise some practicals for paper 1, I would choose 4, and we'll cover them in this lesson. First of all, required practicals are extremely important in each paper because apart that they give you a lot of background information on the topic and how you're actually asked to apply the knowledge, but it's also at least 15% of the overall assessment of A-level chemistry, which will assess knowledge, skills, and understanding of the practical works. So it's definitely worth to look at it. So in every specification, whichever exam board you're doing actually, will have a list of apparatus and techniques that you might have used at school. And I would highly suggest you to revisit it just because if you're asked to like design an investigation like this, you can, visualize the actual instruments that you've used at school. And if you haven't done some of these practicals, then it's even more important that you look at the apparatus so that you can really visualize doing this required practical. Okay, and I'm not going to go through the whole list, but I will want to be more concise. Okay, anyway, remember that you also have all the list of the required activities that you need to do for each exam board, which are actually very, very similar. That is why I chose 4 specifically for today. For paper 1, the most important ones would be to make up standard solution and carry out acid-base titration. Measure enthalpy change. Well, I hope that those are generally simpler, but we're still going to look at the challenging parts. Measuring the EMF, this is very important because when you study the electropotential topic, you're asked to draw out the cells, and this is really the practical part. Investigation pH change as well is really closely related to the titrations, of course, and a very interesting one would be the identify transition metal ions. Okay, so this is for paper 1, and notice how also different exam boards have really the same practicals. In fact, this is at Excel, and this is OCR. Okay, and all of these are tested in paper 1. So this gives an important information, which I talk about always so much, that you should try different exam boards. Okay, but let's get started into this alternative revision of practicals because we'll do it by doing exam questions. Now, if you're watching this video later, pause it and try the question fully because when you play, I will be going through the answer. Well, part of this question is 8 marks, so I hope you took about like 8 minutes for it. Yeah. The standard solution, okay, require calculations, right? Because you have to be very specific on the amount that you include. So the steps for standard solutions, we have measuring an accurate amount, of solid, and well, you really want to think about not losing any of your substance. So you're going to have to, for example, dissolve it into a bit of water in a beaker and then pour it in the funnel while you wash it with the water bottle, so you make sure that everything is transferred in the volumetric flask. And then remember, there is a specific way to get to the end, that is using drop by drop a pipette, so that you can get the bottom of the meniscus on the measuring line. In fact, notice where the marks are. Of course, here we have an initial calculation. Double check here, pause if you need a bit more time, and you have the mass. Okay, those are all of the information that you're given. That will result in a specific mass that you need to dissolve. Okay, notice the mark: dissolving distilled water in a beaker, transfer to the volumetric flask, and then important, ensure that all the solution is washed out. This mark, notice that it comes together in the explanation, so make sure you mention it. So washing, transfer to volumetric flask. This is with the funnel. And then make up the solution with distilled water, and then mixing. Of course, it's very important several times so that when you use the standard solution, you will have an even distribution of your solute. Okay, very, very important to mention these 2 marks. And here, of course, many marks were for the calculation. And so standard solution, this is particularly difficult exercise that comes, but otherwise you could easily have another like 4 marker where you're just asked to describe, but expect some calculations from this. So when you read the question, yeah, try to identify that it is a standard solution that you have to describe. And this is it for the standard solutions, because I hope you understand the steps, because they're not any different. So we're going to look at an enthalpy change. Okay, and for the enthalpy change, well, the calculation is relatively simple. However, this example, it's one of the trickier ones, and please pause and read it and see if you see when what I mean by being a bit trickier. This is a pretty straightforward calculation to apply the heat change equation. But remember that it could be part of a bigger question that tests the practical. In fact, I mean, just to revisit a little bit, remember, this practical is carried out in a insulated, and very often you're asked to spot where like why your value is different than the one obtained. So you would always have to think about the losses of heat in your apparatus and how to improve it. Okay, and then I hope you got the correct calculation. What I say about could be tricky is the part where you're mixing a solution, because you're gonna have to make you have to make sure to add up the volumes, and then, well, volume, we are given the density, that's why it's the same as the mass. Okay, and then also when you have to calculate the moles, okay, you need to calculate the moles of, generally is the limiting reactant that you have. Okay, that's why it would be the moles of the hydrochloric acid. And then you would calculate the enthalpy. Okay, so heat change equation to find the joules, convert it into kilojoules, and then divide it by the moles. I hope you got the right answer. Now, the question that we will do now, it is like the more challenging part of these enthalpy changes require practical and things that you can discuss. So pause and try to solve it. The solution. So the most common reason of experimental value being different is that there is heat loss, but we have some others, okay? Incomplete combustion is not allowed in this case. It was a very specific example, but most of the time you can also say about the, notice that you're given it the standard conditions, so it could be that it's different than standard conditions, or it could be that the reaction doesn't go to completion, okay? This would also result in a different one, okay? So those normally are the reasons. Now, this is the like kind of application or interpretation question, which can be very tricky, okay? Because, and I've seen this in some calculations, and it makes it quite difficult, because you needed to consider, and here, if you read the question, you notice that, wait, refers to the formation of carbon dioxide, gas, and water in the gaseous state. How would it differ if it's in liquid state? If you think about it, it's all done in standard conditions. Standard condition is 25 degrees, which means that water at 25 degrees would be liquid. But in the combustion, or better, in this specific reaction, yeah, for this, which is this one, the book value is given for gaseous state. So remember that there is a change between the water in a gaseous and a liquid state. This is called enthalpy change of vaporization. Okay, and in fact, I would say that, well, it's going to be more exothermic, more negative. Yeah, because, well, the vaporization, if you think about, if you go from liquid to gas, you're breaking the hydrogen bonds. Okay, so it's going to be an endothermic process. But in this case, the direction that it's asking is from gaseous to liquid. Yeah, from gaseous state to liquid. So it's an exothermic process, because you are you're instead making these hydrogen bonds. So energy would be released. Or think about the energy changes from liquid to gaseous state, how they're different. Okay, in fact, I noticed that the explanation also allows to say, well, water molecules have more energy in the gaseous state, so they have to give away some energy to reach the liquid state. Tricky question, and is even trickier when we have to apply it to calculations. The third practical that I would choose to revise if I had to would be the EMF, because you need to, notice is also asking in this way, outline an experiment to set up the measurement, or you could just be asked to draw the cell. Okay, but either way, this is it's directly linked to the practical skill. So pause the video and make sure you draw it with the nice labels. Let's see if you got the right labels. Now, this is what it looks like. We always have two cells. Very important, the salt bridge. And remember that the electrodes, they're connected by a voltmeter. That's how we measure it. So the tricky thing here could have been to realize that one of the systems, so the ion one, we have two solutions. So the redox occurs between two ions, meaning that we need a platinum electrode. And the standard conditions, you would have to mention that they are all, well, 208 Kelvin, 100 kilopascals, and very important, 1 mole per decimeters cube of every solution. And the electrolytic solution of the ion cell would be a mixture of the two ions. And then notice how you also get a marker for completing the circuit, because remember that the ions flow around the salt bridge, so they complete the circuit. Okay, so notice that there is a bit of drawing involved. And this is, I would say, the practical part of the EMF. Of course, then the reasoning part, it's always relative to discussing the strength of reducing an oxidizing agent. But I made many other lessons on this, so you can go and check them out if you don't feel confident with the calculations. Because I would like to go right away in another practical that I would suggest you to revise. Titrations and measuring pH. And here is the topic of titration curves. I highly suggest you to revise the theory of it, because the practical part, I think you should, at this point of the year, you should be very confident with it, because very often it involves the preparation of a standard solution, which is what we have right here. And then, well, the titration, it's always the same with measuring with a pipette. Normally it's 25 centimeters cube of a solid. Add an indicator, we can never forget it, and then add the other substance in a burette. So of course, it's very important to describe carefully what happens between step 3 and step 4, which is adding it until there is a color change. Now, it's important that if you have to design experiment or describe how you would finish a titration, you could also say that you do a rough titration, so that you know more or less when to slow down adding the volume. Adding the solid from the burette, because closer to that change, you slow down and add drop by drop. All of it while mixing, so it's very important that you mention that too, because it's only when the whole the solution actually changes. Okay, so experimentally speaking, I think it's the easier part. The concept, although the trickier ones are discussing values of that you get from the titration. I'll show you a question very soon. And the other one would be the more technical part of titration curves, which is indicators. So let me show you. Let me read this question for a moment. So this titration, it's a quite specific one, and involved the release or the reaction, releasing iodide ions in the conical flask. So will be iodine that will result in a change in color. And as we know, when iodine is present, there is one indicator that it's very important. And that is starch. In fact, For this titration, and you may remember it as always the thiosulfate and iodine titration, you would add starch near to the endpoint because the chain will be blue to colorless. Anyway, this was specific and I didn't give you the overview. What I want to highlight is how to choose the indicator. And here we have a big list. I would highly suggest you to just remember a few of them. So the most common ones are methyl orange. No, actually, this methyl orange, not this one. And maybe methyl red. There are some others that you're also, for example, this blue one. But the ones that I would suggest you to remember are phenolphthalein, and methyl orange. Okay. Anyway, it's likely that you're given a list of this indicator and you have to discuss which one would be suitable. So notice that the change in color is within a range. In fact, this is called the pH range of an indicator. The endpoint of titration must be within the range of your indicator, because if the color change is like a pH 3 here, phenolphthalein is not going to be useful. It's not going to show any color change. That's why it's very important that you know how to work out the endpoint of titration, and that is given always. So remember, if we measure the pH, and we have the pH is here on the side, and here we have the volume of could be, for example, of sodium hydroxide. In a titration with hydrochloric acid, we would start with a pH very low, and then it would, suddenly we would have a very high pH. Okay, and here we would form it like this. So we would have several points, and then we would do tangents. And the vertical part, the middle of it, it would determine the endpoint of titration. And well, if we have also, we should know that when we have like strong acid and strong base, this is going to be at 7 because it's neutralized. When we have weak acid and weak base, then it's different because there is the salt of so the conjugate acid or the conjugate base that will have an effect on the end pH. And I made other videos for it, so I invite you to watch that to revise the whole topic. Okay. And so the point being is in like practical skills that you could be asked for the titrations, and they're a bit more challenging, is definitely the part of the indicator. And when we talk about the like what I mentioned before, that sometimes you're asked to discuss the values. This could be like a tricky one. The point being is try to understand the value of the titer that you get, and if there is any factor that is changed, how would it affect that titer? So please pause the video, take a moment to read these and try to answer before I give you the solution. I know this is a tricky one. So the correct answer is D. Now, let's think about it. First of all, the smaller, so this is the smaller titer would mean that, so think about it. It doesn't mean that you have a more concentrated or more diluted solution. Okay. So if it's smaller titer, it means that you have you've required less volume in your burette to neutralize whatever is in the conical flask. So if you rinse the pipette with water before filling it with sodium hydroxide, you're gonna have less sodium hydroxide present because there is also more water in it. And that's why you will need less titer, or you would need a smaller volume of hydrochloric acid to react. And that's why the smaller titer, because you have less. If you had a more concentrated, you would, I think, I know it's tricky, but always think about what is the consequence of that action on your values. And then hopefully this can help you getting to the answer. If I had to revise another practical for paper 1, I would choose the transition metal ones. Now, the practical, to be honest, to design an experiment, I think it's not too difficult because you know the instruments that you use, because you would simply mix the solutions, okay? What is a bit more difficult is this type of questions where you're given 3 different investigations or three different reactions, and you have to work out what the conclusion means. Okay, so this is a really nice 6 marker for you to try. So pause the video and really give it a go with all of the structures and the appropriate calculations. Okay, I know it's also very difficult to remember transition metals color, which means that if you needed to check your notes, please do that. Okay, so that you can, revise the topic at the same time. Okay, when you're ready, play, because I'll be going through the solution. Now, it's a lot going on, and it's not very clear because it's just so wordy. So one thing that I would do before I work out the solution is try to make it a bit more visual. So what this means is, okay, you would write down the actual equation before even you do the product. I think it's much easier because like this, you can really visualize what happens. So for example, as you read the reaction 1, you have so copper sulfate reacts with excess aqueous ammonia in a ligand substitution reaction. It's this one, copper sulfate. Now remember that it's still an octahedral complex surrounded by water. The sulfate is what neutralizes the charge of the complex. So when it reacts with ammonia, we have this substitution. Okay, how is it possible that it's a trans-isomer? Well, draw it out. It's very important, and I always suggest you to start from this skeletal structure of the metal, and then you can add around it the groups. Okay, so the trans-isomer, because notice how the direction of the dipole given by the water goes in opposite direction. That's why it's a trans. Okay. Second reaction, I would suggest you to do the same. Start with the equation, and this is the correct one: copper oxide, hot sulfuric acid, disproportionation reaction. So sorry, just copper oxide. Remember, this is a solid. That's why it's neutral. It's a compound. Okay. And so we have the disproportionation reaction, and also the solutions, the color would help you telling you, okay, what is it? What is it formed? Okay. And the oxidation numbers, they change. So disproportionation reaction because the same. So copper is both oxidized and reduced. The third one, once again, I will start from the equation. Here is the correct one. Again, we have copper oxide solid reacts with the nitric acid. It's simply a neutralization reaction. And then dehydrated salt, well, we know the calculations for water of crystallization. It's kind of like an empirical formula. In fact, we start with the molar ratio. The molar ratio would give you your formula, and then from the empirical formula, you need to work out the number of waters. So here is just about like counting the number of atoms and realizing how many waters are present. Okay, definitely a tricky question, and I hope you got at least some of the marks. Otherwise, I hope this was a good experience to see how these practical skills can be tested in this topic, which I think are a bit more challenging one. Okay, so thank you so much for joining this practical skills revision, and I hope you got some good exam practice, and I will see you for one on paper 2.